Welcome to the first session of our four-part series titled String Graphs. This series explores how the humble straight line can produce aesthetically pleasing images. This family of straight lines is being formed by connecting multiples of 2 around a circle. This family of straight lines is formed by connecting multiples of 3. What do you think the multiples of 4 might look like? Architect, artist, engineer Santiago Calatrava has brought this beauty to life in cities all over the world. The cables of the Margaret Hunt Hill Bridge in Dallas, Texas connect the roadway to a parabolic arch. A simple but equally striking example is his Alamillo Bridge in Spain. And, just in case you're not impressed enough, amongst his other works is the Milwaukee Art Museum. The outstretched wings actually open and close to control the lighting in the building. In this session, we will use linear graphs to imitate the patterns found on the Cords Bridge in Jerusalem. And just in case you hadn't guessed it, it's another of Santiago's great works. Straight lines can be represented in a number of ways. In this session, we will focus on what is often referred to as the gradient and intercept form of a straight line. Each component of the equation has a name and purpose. X is the independent variable. Y is the dependent variable. M is the gradient or slope of the line, and M is referred to as a parameter. C is the y-intercept. C is also referred to as a parameter. The point on the line has coordinates x and y. As the point moves along the line, x and y change, but the parameters m and c remain constant. Now I will change the equation to the line by changing the gradient, that is, parameter m. Now that this value is locked in, the variables x and y have a different relationship, but they're still variable. Now I can change the equation by changing the y-intercept, that is, parameter c. Now that this value is locked in, the variables x and y have a different relationship, but as you can see, they can still vary. So, our parameters are characteristics of the equation. They define how x and y are related. We are now ready to determine our first equation. The first question on the assignment sheet requires us to find the equation to the line passing through the points 0, 10 and 1, 0. The point 0, 10 is on the y-axis, and 1, 0 is on the x-axis. I'm not going to solve this problem. Instead, I will solve a similar one. I will determine the equation to the straight line passing through 0, 10 and -2, 0. The question provides us with the y-intercept, so the c in our equation is equal to 10. Now we need to determine the gradient. The gradient of a straight line is calculated as rise over run, which is given the formula y2 minus y1 divided by x2 minus x1. So you can use the coordinates and substitute each value. In case you're wondering, it doesn't matter which coordinate pair you use as 1 and 2, but you have to be consistent. It's time to enter our equation on the calculator. I'll start a new document and insert a graphs application. The page number tells us that this is problem 1, page 1. The assignment sheet tells you to view Quadrant 1. Well, important characteristics of my graph are also in Quadrant 2, so I'm going to make some changes. I could simply drag the screen downwards, or type in Windows settings in the Window menu. However, I'm going to change the values directly by clicking on the maximum value for Y. I need it to be 10, or at least 10, so I can just add 4 to the current value. And to keep the window aspect ratio square, I'll do the same to the Y minimum value. You may wonder what it's meant by square. You can see the grid is square. That means 1 unit in the right, or 1 unit in the positive X direction, is the same as 1 unit up, or in the positive Y direction. To graph our first line, we can press Tab or Control and G to view the graph entry line. You'll notice that there is an expression, f1 of x equals. For our purposes, this is the same as saying y equals. So I can enter the equation 5x plus 10. Read that as y equals 5x plus 10. Suppose my next equation passes through the points 0, 9 and -4, 0. We can do the same calculations as we did before. The y-intercept is 9 and the gradient is 9 divided by 4. I can enter this equation in the graphs application as f2 of x. Remember, you can just press the Tab key or Control and G. You'll notice that the equation labels start to build up on the screen. If you're finding this a bit messy or distracting, you can change the settings to automatically hide plot labels. If you want to check an equation at any time, you can simply hover the mouse over the equation or return to the graph entry line. The color of the graph matches the colored box on the left of the corresponding equation. You'll also note that the graph is automatically highlighted. If my next equation passes through the points 0, 8 and -6, 0, we can do the same calculations again. The y-intercept is 8 and the gradient is 8 divided by 6. I can enter this equation as f3 of x. You may notice that I've left my gradient as 8 over 6. This does simplify to 4 over 3, but for now I'm going to leave it as 8 divided by 6. Now that I have a couple of graphs, I can try and predict what the next line might be. You can pause the video to think and predict. The next equation passes through 0, 7 and -8, 0. So the next equation will be 7 divided by 8 times x plus 7. You can see the string pattern starting to form, similar to those on the chords bridge. In the strings activity, you need to finish all the equations and place them in a table. That will help you identify the patterns. The next part of the activity invites you to determine a general equation, one that involves a parameter. The parameter relates the equation number to the y-intercept and also to the gradient. In this family of straight lines, as the equation number increases, the y-intercept decreases. For equation 1, the y-intercept is 10. For equation 2, the y-intercept is 9. Equation 3, the y-intercept is 8. I can see that if I added the equation number to the y-intercept in each case, I would get a value of 11. So I can flip this relationship, or transpose it, to say that the y-intercept is equal to 11 minus the equation number. Now I need to do something similar for the gradient. Most of my gradients have been written in fraction form, so that allows me to look at the numerator and denominator separately. I'll start with the numerator. With the exception of the first gradient, the numerators have the same value as the y-intercept. But if you look back at the very first gradient, the calculation was 10 divided by 2, which simplified to 5. So it actually does fit the pattern. So we need to be careful. Simplifying the fractions can actually make it harder to identify the patterns. So, for the numerator, in the gradient, I can use the same expression as I did for the y-intercept. I can express the numerator as 11 minus n. Now let's have a look at the denominator. It went from 2 to 4 to 6. These numbers are double the equation number. I can express the denominator of the gradient as 2n. Now I've expressed the gradient and the y-intercept in terms of the equation number n. I can therefore define all my equations in terms of n. I'll insert a calculator application. Notice this is page 2 of problem 1. I can define my equation as follows. f of x, n equals 11 minus n, that's the numerator, over 2n, our denominator, times x plus 11 minus n. Now, let me check. If I want to see the first equation, I can type f of x, 1. I see the expression 5x plus 10. If I want to see this as an equation, I can type y equals f of x, 1. So, that's a good start. Let's check the second equation. Y equals f of x, 2. Looks like everything is working. If I want to check all the equations at once, I can store the equation numbers 1, 2, 3, all the way up to 10 into n. Now, I'll go back to my graph application on page 1.1. I'll make a bold decision to delete all of my equations. In the activity, you are instructed to put them as a new problem. That way you don't have to delete anything, and you can submit that work to your teacher. Now, I can enter my general equation, f of x, n. It's kind of a bit like a copy and paste. The calculator knows how this function is defined, and we've set values for n. So we see the family of straight lines. These lines resemble those of the chord's bridge. That's all for this session. Make sure you work through the questions on sheet 1. You can use this video as a reference. When you finish the question sheet, check out sheet 2. In sheet 2 we stitch some other lines together to form a new family of straight lines. Thanks for watching.